going to see a topic on conducting polymer, especially polyacetylene, preparation properties and uses. I am Dr. S. Rekha, Associate Professor, RMD Engineering College, Chennai. Let us get into the topic. Conducting polymer, as the name indicates, any polymer which can conduct current is called a conducting polymer. For a polymer to conduct current, it should have free-flowing electron. To have a free-flowing electron, it needs pi electron cloud, that is delocalized pi electron. So when a polymer is going to have an extended conjugation, then it is going to behave as a conductor, electrical conductor. Example, we have polyacetylene, then we have polyaniline, we have polythiophene, etc. Okay, let us know the conductivity range of any material, right? So this region, if you see, it is an insulator 10 power minus 18 to 10 power minus 8. So it behaves like an insulator, conductivity in Siemens. Okay, so semiconductor region is 10 power minus 8 to 10 power 0. Right, conducting range is greater than 10 power 0. Up to 10 power 6 we have conducting region. So we have a class of polymer called electroactive polymer. Okay, so these polymer composites or blends behave like a semiconducting material. Electroactive polymer behave like a semiconducting material. Some cases they also behave like an metallic conductor. So we have a separate class of conducting polymer, okay, which may be in its pure form, it may be an insulator, but when a dopants are introduced, it is shifting towards to the metallic conduction zone. One example is polyaniline. To prepare a conducting polymer, what is required? So we need a linear polymer backbone. Okay. Polymer with extended conjugation is the next condition. Third condition, a dopant to be introduced for charge carriers, right? So we have different conducting polymer, namely polyphenylene, polypyrrole, polythiophene, polyphenylene vinylene, polyacetylene, and polyaniline. These are few examples where we have double bonds. Everywhere we have conjugations, right? This conjugation, this pi electron cloud makes it to be conducting in nature. So preparation of polyacetylene. So we have acetylene vapor which is passed over the Ziegler-Natta catalyst. Okay, so it produces a trans form of acetylene. See here, trans form of acetylene. This, when undergoes isomerism, it gives you another product called cis isomerism, cis polyacetylene. So see here the structure changes, right? Okay, so these are pure forms which behaves like an insulator. So we have to introduce the dopant. So if we introduce p-type dopant, the p-type dopant examples are halogens, right? This is arsenic pentafluoride. So these dopant act as an electron abstracting group or Lewis acid group. So it takes up electron from there and creating a positive charge on the polymeric body. Let us see in detail with the mechanism. Polymer are doped with electron accepting groups such as Lewis acid, example iodine gas in CCl4. Let us see with the structure. So this is what we are seeing is transform of your polyacetylene. So it is a neutral molecule. Okay, when we introduce iodine vapor, okay, this bond which is having two electron, one electron is taken by the iodine molecule, so it's an electron accepting group, leaving behind one electron. So one carbon atom takes the positive sign, another carbon atom takes the radical form. Okay, so this is called polaron. Okay, so now when I introduce second iodine over the surface, so what happens? Similar mechanism, we get two positive charge and these two radical ion, they form a new bond. See, in red color we have indicated, it forms a new bond. So this is called bipolaron because it carries two charges. Now these charges can travel by shifting the electron, right? So now electrons are moving inward and the charges, positive charge is moving outward. See here. So it is called soliton. The structure is called soliton, right? Let us see the overall mechanism. So we have the neutral molecule and here we have the conduction band as well as valence band, right? The gap. So now when I introduce iodine, what happens? It accepts the electron. One electron is accepted and one charge carrier, that is positive charge carrier, is developed and that is called polarin, right? Now when I introduce another iodine, okay, another iodine, so that develops an energy level, right? So another charge is produced. See, at the energy level we have two positive holes, so that is bipolar, then undergoes a reaction to give the soliton where the charge, positive charge moves outward, the electrons move inward. See here, three new bonds are formed. N-doping. So it is similar to p-doping. Here Lewis bases are used which will donate electron to the polymer chain. So we will see as a summary. It's similar to that of polymer n-doping. Okay. So here the p-dopant dopant is sodium naphthalite. Okay. So here when this is introduced, what happens? Again, it gives one more electron. Okay. So this becomes excess in electron. So carbon gets a minus sign, leaving a radical. Okay. So when again this dopant is added, so again one more, see here, one more negative sign has come. Okay. Near the arrow mark, we have the negative sign. Let me take the pointer. Yeah. So here we have one negative sign and another negative sign is here. Okay. By giving donated by this sodium naphthalite. Okay. So now what happens after this? So again this is called polarin. With one sign it is polarin. Two negative sign it is bipolarin. Now this negative sign is moving outward, right? The electrons are moving outward. So what we can see here, minus sign is there. See, new three red bonds are formed and this is soliton. See here, from valence band to conduction band. So there is a energy level created and this energy level is negative. Since it is negative, electrons are present. So two electrons for each negative ion charge. Okay, this is for one negative charge, this is for another. So now from here to conduction band, jumping is easier. So they behave as a conducting polymer. So either you can add a p-dopant or you can add a n-dopant. See here, a comparative statement of conduction band and valence band. In neutral, so conduction band, neutral solution, okay, after doping. So before doping there is no energy level. After doping there is an energy level created. For positively charged, this electron is taken away. Okay, for negatively charged, one more electron is given to this. So we have the charge. This is for soliton. Properties of polyaniline. So it shows a high electrical conduction, right? In its pure form, it is an insulator, but with dopant, it behaves like a conductor, right? Okay. Mechanical property. So it is brittle and flexible material. Thermal stability. Polyester is thermally unstable, especially when exposed to air. When it is exposed to air, it reacts with it. Solubility, it is insoluble in various solvents, making it challenging to process in solution form. Then it forms a conductive film. It is used in battery technologies. It is used in sensors. It is used in electronic industries, being a conducting polymer. In short, light emitting diodes is prepared with it. Water purification devices are prepared with this. Hydrogen storage devices in biosensors and printed circuit boards, all these polyacetylene is used. Thank you, students. Let us meet in another class.